Problem number 22. A bullet of mass m1 strikes a pendulum of mass m2 suspended from a pivot by a string of length big L with a horizontal velocity v0. The collision is perfectly inelastic and the bullet sticks to the bob. Find the minimum velocity v0 such that the bob with the bullet inside completes a circular vertical loop. So first of all, we can draw the picture of this scenario. On this picture, first bullet stick this pendulum and getting a new velocity v1. After that, it start to rotate till highest point, where it's getting speed v2. And the best way to do this problem is to probably to go backward. So first we have to find how much is minimum velocity v2 we can get here, not to fall down, because we have string, not a rod. So it means that it's not enough to have zero velocity here. This velocity must be such a way that there is no negative tension in this string. So critical value for this string is 0. So we can write equation for this motion on the top. So we have MA equal mg plus tension, where m is total mass of bob and bullet. In a critical scenario, tension must be equal 0. It means that acceleration in the highest point is g. But we know that if body going by circular orbit, acceleration is centripetal acceleration, and we can calculate this acceleration by this way. So this is the connection between velocity in highest point and acceleration. So next step, if we know what is velocity in the highest point, we can find what is velocity in the lowest point right after collision. So we have to find what is velocity v1. For that we can use energy conservation. It means that kinetic energy in highest point plus potential energy compared to lowest point, that's equal to kinetic energy in the lowest point. So here we can use this expression substantiated here and find that v1 square equal 5gl. And the last step is to find what is initial velocity v0, because here we have absolutely inelastic collision. We have momentum conservation here, and we can write this equation. This is the equation for momentum conservation, and from here, using this expression for v1, we can find finally that v0 must be equal to this expression. So this is correct answer. v0 equal m1 plus m2 multiplied by a root from 5lg and everything divided by m1, which is E, correct answer. Problem number 23. Consider two uniform spherical planets of equal density but unequal radius. Which of the following quantities is the same for both planets? A. Escape velocity from the planet's surface. Let's see. First of all, we need to count what is mass of this planet using equation n equal volume multiplied by density. After that we can find the force of gravity right on the surface of this planet. So this force equal this expression, where m small is mass of our object. From this formula we can find what is the acceleration of free fall right on the surface of this planet. As we can see, this acceleration proportional to radius for the same density. And after that we can find what is the escape velocity from the surface of planet using this equation. We know that escape velocity equal root 2gr, or after this substantiation we can take this formula. Here we see that escape velocity proportional to radius, so it means that it's not the same for both planets with different radii. Part B, the acceleration due to gravity at the planet's surface. We see that this is not true again, because this acceleration is proportional to radius. Let's check part C, the orbital period of a satellite in a circular orbit just above the planet's surface. We know that orbital speed right above the surface we can count using this formula, and the period we can find, that's a distance over speed, 2 pi r over speed. And we see that using this substantiation we can find that this speed again proportional to radius, so radii are cancelled, and finally we have same period for any planet with the same density. So C is true. D, the orbital period of a satellite in a circular orbit at a given distance from the planet's center. This is not true, because each planet has a different mass, and on the same distance, if mass is higher, we have a higher orbital velocity. That's it. In this problem we have C correct answer.